Hey everyone, have you ever stopped to think about how we get a computer, a machine that only really understands ones and zeros, to grasp something as complex and messy as human language? It's a huge puzzle in AI, and it all begins with one absolutely critical step: getting our data ready.
So yeah, how do you teach a machine to read? It's not like it can just curl up with a good book. Machines don't get nuance, they don't get sarcasm, they don't get poetry. They get numbers. And the entire magic of natural language processing, or NLP, is all about building a bridge between our world of words and their world of numbers.
And that's exactly our roadmap for today. We're going to start with that fundamental language barrier, then we'll get our hands dirty with a real-world dataset, dive into the art of tokenization, figure out how to do it at scale, and finally, put the finishing touches on with perfectly padded data batches. Let's dive in.
All right, first things first, we have to really understand the core problem here. It's like our model and our data speak two completely different languages, and it's our job to be the expert translator. See, on one hand, you have these incredible models, like BERT. They are absolute beasts of mathematics. But at the end of the day, they only understand one thing: tensors, which, are just fancy lists of numbers. But on the other hand, we have our data: articles, emails, tweets, messy, beautiful human language. They can't talk to each other directly. Our entire mission is to turn that text into the numbers the model can actually crunch.
Okay, enough with the theory, right? Let's make this real. We're going to work with an actual data set to see how this all plays out. So let's meet our subject for today, the MRPC dataset. The MRPC, which stands for Microsoft Research Paraphrase Corpus, is a total classic. It's basically a collection of just over 5,000 pairs of sentences. And for every single pair, there's a label that tells us if the two sentences mean the same thing, if they're paraphrases. It's a fantastic little data set for getting a grip on these core ideas. And this table gives us a perfect little snapshot. Take a look at that first row, index 0. The two sentences are really similar, right? Accused his brother versus said his brother. So it gets a label of 1 for equivalent. Now jump down to row 15. The show's stars and the show's producer. Totally different meanings, so that gets a label of 0 for not equivalent. The whole goal is to train a model to figure this out on its own. So where do you get this data? It's super easy. You can just grab it from the Hugging Face hub. It comes all nicely organized into a training set, a validation set, and a test set. Think of it like this. We use the training set to teach the model, the validation set to give it little quizzes along the way, and the test set for its final exam. Okay, so we've met our data. We know what it looks like. But how do we actually do the translating? Well, that brings us to the really cool part, the art of tokenization. This is where the magic of turning words into numbers happens. Now, we can't just randomly turn words into numbers. A model like BERT is, well, it's kind of picky. It expects the data to follow a very specific recipe, especially for sentence pairs. It wants a special CLS token right at the start, then the first sentence, then a SEP, or separator token, then the second sentence, and finally one more SEP token to close it all out. But wait a minute. Once we've squished all that together, how does the model know where sentence 1 stops and sentence 2 starts? That's where this really clever little trick comes in, and it's called token type IDs. And the logic here is actually beautifully simple. Just look at this. Every single token that belongs to the first sentence, and that includes the special CLS and the first SEP tokens, gets a token type ID of 0. Then, everything that's part of the second sentence gets a 1. It's like leaving a trail of breadcrumbs for the model to follow. So, let's just hammer this point home. These token type IDs aren't just extra data. They are absolutely essential instructions. They're what guide the model so it can understand the relationship between the two pieces of text we're feeding it. Awesome, so we have our recipe down for one pair of sentences, but our dataset has thousands of them. We need to do this at scale and, preferably without our computer catching on fire. And this is a super practical problem. If you try to load a massive dataset into your computer's memory all at once to process it, well, you're gonna have a really bad time. So how do we work smarter, not harder? Well, the slow way, the brute force way, is to just loop through the dataset one by one. And yeah, it'll work, but it is painfully slow. The efficient way, the pro move, is to use the .map method from the Hugging Face datasets library, and specifically to use the batched equals true option. This lets us process huge chunks of data all at once. And when I say faster, I'm not kidding. The performance boost is massive. This isn't just some small tweak. We're talking about making your pre-processing 10 times faster, maybe even more. For any real-world project, that's a total game changer. So what's the magic behind .map? Instead of loading everything into memory, it works directly on the dataset file on your disk. It applies our tokenization function to big batches of sentences at once, and it even adds the new columns, like our input IDs, right back into the dataset for us. It is fast, it's memory efficient, and honestly, it's just really elegant.
We are so close. We're on the home stretch now. We just have one last crucial step to get our data perfectly ready for training. We need to create perfect batches.
And here's the final puzzle piece we have to solve. In any group of sentences you pull from your data, they're all going to have different lengths, right? But models need every input in a batch to be the exact same length to process them efficiently. So, what do we do?
The answer is this really smart technique called dynamic padding. Now, the simple but kind of wasteful approach would be to find the longest sentence in the entire dataset and pad everything to that length, but that's so inefficient. Dynamic padding is way smarter. For each batch, it just finds the longest sentence in that batch and pads everything else up to match it.
This table makes it super clear. Imagine in one batch, the longest sentence has 67 tokens. Okay, so a sentence with 32 tokens gets padded up to 67. One with 55 tokens gets padded up to 67. And the one that's already 67 tokens long, it gets no padding at all. This saves a huge amount of pointless computation.
Now, you're probably thinking, okay, that sounds like a headache to code myself. And here's the best part. You don't have to. The Hugging Face Transformers library gives us this amazing tool called a data collator with padding. You literally just give it your tokenizer, and it handles all of this dynamic padding for you automatically. It's that easy. And just like that, we've done it. We've gone from raw human words to perfectly structured, numerical, and efficiently batched data that's ready for training. We've successfully translated human language into machine language. So the only question left is, with data this perfectly prepared, what incredible secrets will it teach our model?